So thank you very much for joining the research seminar brought to you by the Central Bank Research Center of Asia School of Business. I'm Mikuo, and I'm going to be your host today. And we have a wonderful speaker, Daniel, from the University of Massachusetts Amherst. And the talk will be an hour as we scheduled from now. And for the online participants, please feel free to leave questions on the chat. And I hope there are some chance to take some question in the end, if time remains. Okay, so the today's talk, the research Daniel is going to show us is a very, very hot area in empirical research. And I'm very excited to learn the cutting edge technologies. So the paper's title is A Local Projection Approach to Difference and Differences Event Studies. Okay, the floor is yours, Daniel.
Thank you so much.
Could you also share the screen, please?
Yeah, let me share my slides. There you go. Do you see my slides?
Yes, we can see your slides.
Okay, great. Thank you so much. Thank you all for being here, and thank you, Equo, for the organization and the introduction. It's a pleasure being here. I know it's evening for you, it's early morning for me, and this paper that I'm presenting is called The Local Projections Approach to Difference in Differences Event Studies. It is co-authored with my colleague at UMSM, Sterin Dube, and with Oscar Jorda and Alan Taylor from UC Davis. The topic of this paper is how to estimate difference in differences when there are different groups that enter treatment at different points in time. There is a recent and growing literature that has studied this question, and this literature has shown that there are serious problems with the two-way fixed effects regression that has typically been used in this setting. So in this paper, we propose a way to solve these problems, which is based on a new regression-based framework. And basically, our framework combines local projections with a clean control condition. Local projections is a way to estimate dynamic effects in a flexible way that has been proposed by one of our co-authors, Oscar Jorda. And this clean control condition is something that we add in order to avoid the problems that fixed effects estimators can suffer from in this setting. So we call this approach that we propose LPDID, as in local projections, difference in differences. After presenting our proposed estimator, I will present evidence from Monte Carlo simulations about the performance of our estimator in some common setting, including in comparison with other estimators for difference in differences that have recently been proposed in the literature. And then I will also present two empirical applications in which we use our LPDID estimator to study the effect of banking deregulation on the wage share and the effect of democracy on growth. But before I move forward, I want to address a question that some of you may be asking, which is why do we need another difference in differences estimator, given that in the last years, several estimators have been introduced in the literature to address the problems with two-way fixed effects regression and to address the different settings that can arise in a difference in differences method. I think that there are advantages to the method that we propose. It is simpler and more transparent and easier to code and to compute relative to other estimators that have recently been proposed. It is more flexible because it offers a general framework that, as I will show, it's easy to adjust to accommodate the different settings that can arise. And third, a big advantage of our LPDID approach is that it allows to control for pre-treatment outcome dynamics and other time-varying covariates, which is something that most of the estimators that have been recently proposed in the literature are not designed to do. Now, let me take a step back and talk about, the issue that we are addressing here. Difference in differences is one of the most popular methods in applied economics. In the simplest 2x2 setting, as illustrated in the example in the left panel here, we just have, we just compare changes in the outcome between a treated group and one control group around the time of treatment. However, what is most common is to actually have a staggered setting, meaning that there are different groups of units that enter treatment at different points in time. So here in the right panel in this slide, you have an example with 3 groups. There is one group of units that enters treatment at time t star k, another group that enters treatment at t star l, and then there is one never treated group. Now, until recently, the conventional way to implement a difference in differences design was to use the two-way fixed effects regression. In the static version, this is a regression where we have the outcome on the left side, and on the right side, we have unit fixed effects, time effects, and the treatment indicator. In the dynamic event study version, we also have leads and lags of the treatment indicator in order to estimate dynamic effects and test pre-trends. So this has been the conventional way to implement difference in differences by estimating one version of this regression. And this is fine in the simplest 2x2 setting, in which there is only one treated group and all treated units enter treatment at the same point in time. However, what recent studies have shown is that when there is staggered treatment with different groups entering treatment at different points in time, two-way fixed effects regression can give biased results, even if all the underlying assumptions that underpin difference in differences, mainly no anticipation and parallel trends, hold. So two-way fixed effects, the two-way fixed effects estimator can give a biased estimate of the treatment effect, even under parallel trends and no anticipation. And this bias arises when treatment effects are dynamic, in the sense that the effect doesn't take place entirely on impact, but there is some lagged gradual response, and when they are heterogeneous, in the sense that the treatment effect may be different for different groups of units. So why is the two-way fixed effects estimator bias? What is the problem? We can see the estimate from two-way fixed effects regression as a weighted average of all possible 2x2 comparisons in the data. We know this from a recent paper by Goodman-Bacon. And these comparisons that contribute to the two-way fixed effects estimate are of 3 types. Comparisons in which newly treated units are compared with the never treated group, comparisons in which newly treated units are compared to units that are not yet treated, but may be treated earlier. But there is also a third type of comparison, which is a forbidden comparison, in which newly treated units are compared with earlier treated units. And I call this a forbidden comparison because it should be forbidden, because this is the comparison that can introduce bias. In this example with 3 groups, this forbidden comparison would be a comparison around time t star l, which is this point in time here, in which the treated group is this group here that enters treatment at t star l, and the control group is the group that entered treatment earlier, the group that is already treated that entered treatment earlier at t star k. So what happens basically with two-way fixed effects regression is that after a unit enters treatment and it serves as the treated unit in the time in which it enters treatment, after that, this unit goes back into the control group and is used implicitly as a control for the groups that get treated later. And it is this type of unclean comparison in which earlier treated units are used as controls, which can introduce bias. And the reason why it introduces bias is that these earlier treated units may still be experiencing lagged effects of treatment, and so they are not good controls. So in practice, any lagged effects of treatment that these earlier treated units may still be experiencing will be subtracted from the two-way fixed effects estimate. It will basically enter with a wrong sign. And Goodman-Bacon also provides a formula for this bias, showing that the probability limit of the two-way fixed effects estimate is equal to the sum of three things. The first is a weighted average treatment effect on the treated, and this is good, it's what we want. Then there is this term here, this is bias from possible violations of the parallel trends assumption that underpins difference in differences, and this is something we knew about, of course. But then there is also this third term here, this delta ATT. This is bias coming from these unclean comparisons in which earlier treated units are used as controls. So this negative term here is the fact that these lagged effects of treatment enter with a negative sign the estimate whenever earlier treated units are used as controls. Another way to see the same problem is to use a theorem by Deschaise-Martin and Dalfeuille, in which they show that the two-way fixed effects estimate can be seen as a weighted average of all the cell-specific average treatment effects on the treated in the data, in which a cell is defined as a treated unit at a point in time. And the problem here is that the weights assigned to some of these group-specific effects can be negative, meaning that a positive effect can enter with a negative sign in this weighted average. And this is just a different way to see exactly the same problem, because these negative weights arise precisely from these unclean comparisons in which earlier treated units are used as controls. So this is the problem with two-way fixed effects regression, and this is the solution that we propose in this work. We propose a local projections specification to which we add a clean control sample restriction to avoid this type of bias. So the way to implement our estimator is a simple regression, and I will show now the simplest version without any covariate, in which on the left side we have the change in the outcome between time t-1 and time t plus k, in which k is the time horizon at which we are estimating the effect. And on the right side of the regression, we have the change in the treatment indicator at time t and time effects. Importantly, you need to restrict the sample to observations that are either entering treatment, meaning that for these observations, the change in the treatment indicator is equal to 1, or clean controls. Clean controls are defined as units that have experienced no change in the treatment indicator for at least capital H periods before treatment and until time t plus k. So basically this capital H is a parameter that the researcher will choose based on context, and it will define the time window for defining clean controls. So what happens here with this sample restriction is that when a unit enters treatment, in the time period in which it enters treatment, it serves as the, it's in the treated group. After that, you drop it from the sample, so it does not get used as a control, but it can go back into the sample after capital H periods. Now, there is flexibility here in the sense that you can set capital H equal to infinity, in the sense that you only allow not yet treated units to be clean controls, or based on the setting, you may want to set a finite value for capital H so that you assume that after capital H periods, any lag dynamic effect of treatment has stabilized, and so that that unit can go back in the control group because its trend is no longer influenced by the effect of treatment. So the role of this sample restriction is precisely to avoid the bias due to the forbidden comparisons in which earlier treated units are used as control. With this sample restriction, you don't allow previously treated units that are potentially still experiencing time-varying lag treatment effects to be used as controls.
Can I ask one question here?
Yes, of course.
The reason why we need this big H here is we have in mind some sort of like dynamic model in our mind.
Yeah, so the reason why we need it is because we have in mind that for capital, that, you know, the effect of treatment does not necessarily occur entirely on impact in the time period in which the unit enters treatment. So here we are assuming that it takes at most capital H time periods for the effect to stabilize. Okay, the effect doesn't need to go to zero, just have to stabilize so that after capital H periods, the change in the outcome, the trend, is no longer influenced by treatment. And as I said, it's, of course, one can just say, you know, be strict and only use units that have never been treated so far as the controls, but there are settings in which that will not be appropriate or possible. Imagine you are studying, you know, the effect of minimum wages. There will be usually no area that has never had a minimum wage increase. So in that case, you will want to make an assumption about after how many periods you can consider the effect to have stabilized and the unit can go back in the control group. Does that answer your question?
Yes, thank you.
Thank you. So one can extend this regression to include covariates, in case one needs covariates, because the parallel trends assumption only holds conditional on some variables or to increase precision. And the local projection specification allows to include lags of the outcome as control variables, and given the structure of the local projections regression, these outcome lags will always be measured before treatment. And the same holds for covariates that can be included. One can include contemporaneous values of the covariates, but also lag values. And again, the structure of the local projections regression will ensure that if you include the lag value of a covariate, this will be measured pre-treatment. So it will be predetermined. Now, if one doesn't like to drop observations and restrict the sample, one can just use an equivalent specification where you use the full sample, but you include interaction terms to rule out, to apply the clean control condition and rule out the unclean controls. So to do that, we can define an unclean indicator variable, which is equal to 1 if a unit is previously treated. And then you just use that indicator as a control variable in the regression, and you interact it with all the covariates, and then the coefficient, the coefficient that estimates the effect will be exactly equivalent as in the case in which you restrict the sample. Now, what does this LPDID estimator identify precisely? Using the logic of the Frisch-Wohlowell theorem and assuming that the parallel trends and no anticipation assumptions that underpin the difference in differences method hold, we can show that our LPDID estimator identifies a weighted average of all the possible group-specific effects in the data, where a group of units is defined as a treatment cohort. Okay, so when we talk about groups here, a group is a set of units that enter treatment in the same time period. So here in this formula, tau G of K is the average treatment effect on the treated for treatment cohort G, K periods after treatment, and omega GK is the weight assigned to that group-specific effect by our estimator. And importantly, the weights that are assigned to each group-specific effect are guaranteed to be always positive, and they sum to 1. Remember that the bias of two-way fixed effects regression can be seen as assigning negative weights to some effects. Here, thanks to the clean control condition, we have no negative weights. And in particular, this is the formula that we derive that characterizes the weight assigned by our estimator to each cohort-specific effect. And you can see that in the numerator of this expression, there are three things. The first one here is the size of a subsample that includes group G and its clean control units. Small n is G is the share of treated units in that group, and this third term here, NCGK, is the share of control units in that subsample. So what does it mean? It means that the weight assigned to a group depends on the size of the group and on treatment variance in the subsample defined by that group and its clean controls. So, this is not surprising, because we know that OLS regression puts more weight where there is more variance. And, so here the share of treated units in the subsample times the share of control units, it's basically the variance in that subsample of treatment. So, it's not surprising that an OLS regression would put more weight where there is more variance. But the thing is that here there is no negative weights, so that what we get is actually a convex combination of all the group-specific effects. Now, in some cases, depending on the setting, a researcher may not be happy to estimate a variance-weighted effect and may want an equally weighted average treatment effect. So in some settings, one may want to assign equal weight to all groups. And given this characterization of the weights, then it's easy to obtain an equally weighted average treatment effect on the treated using our approach, because one just needs to run a weighted regression where the weight assigned to a unit is the inverse of this weight that we characterize here. So using this formula, one can also, by running a weighted regression, obtain an equally weighted average treatment effect on the treated, in case the setting is such that a variance weighted effect may not be, the ideal estimate. Something I want to stress about our approach is that it offers a lot of flexibility. So we like to compare it to a Swiss knife, where you can adjust it to address the different problems that you may have in your data set. And in particular, there are two dimensions of flexibility that I would like to stress. The first is flexibility in defining the treatment and control units. So for example, if you have absorbing treatment, in the sense that once a unit enters treatment, it stays treated forever, then you can be purist about clean controls and say, I will only use units that have never been treated until time t plus k as controls. So only not yet treated units are controls. But if you have repeated treatment, if you have a setting in which units enter and exit treatment pretty frequently, so that it's not possible to use only not yet treated units, I made the example of estimating the effect of the minimum wage as a setting in which that would be the case, Then you can select an appropriate time window of capital H, assume that treatment effects stabilize after capital H periods, and allow units to re-enter the control group after capital H periods. But you can also adapt this specification to a setting in which you have continuous treatment, for example. So what can you do for continuous treatment? With continuous treatment, if the setting allows it, you could define treatment units as units that experience some change in the continuous treatment variable, and define clean controls as units that experience no change in the continuous treatment variable for capital H periods. If you have a setting in which this is not possible because this continuous treatment variable actually changes at all time periods, then you could define treated units as units that experience a large change in the continuous treatment variable, and control units as units that experience no large change in the continuous treatment variable. So these are examples to show that really you can adjust this clean control condition to address many different possible settings. A second flexibility is what I mentioned earlier about being able to reweigh the regression, and given that we know what is the weight assigned to a unit, then we can always reweigh and get the an equally weighted average treatment effect or any weighting scheme that we want. If you have covariates and lagged outcomes, unless you make very specific assumptions in general, that will alter the weights. But if you want to preserve the weights in order to be able to do this, then you can always use propensity score reweighting for controlling for covariates rather than a regression adjustment, so that you preserve the weight. So it's always possible to preserve the weights and do this reweighting. Now, we have run some Monte Carlo simulations to assess the performance of our estimator and compare it with other estimators that have recently been proposed for difference in differences. So our simulated data set has 500 units observed over 50 time periods. We assume a data generating process in which the untreated potential outcome is, just depends on a unit fixed effects and time fixed effects, and we assume some persistence in the outcome. We have a setting with binary staggered absorbing treatment. So once a unit gets treated, it stays treated forever. And we assume a treatment effect that is dynamic. It grows in time for 20 periods before stabilizing. And we also assume that the treatment effect is stronger for early adopters. So in this way, we have both the dynamics and the heterogeneity that can create problems in two-way fixed effects regression. And we ran two simulations. In the first one, treatment is exogenous, so units are randomly assigned to groups that get treated at different points in time. But we also have a second setting in which treatment is endogenous, and in particular, the probability of treatment depends on past outcome dynamics. We assume that the probability of receiving treatment is a negative function of the lagged change in the outcome. So basically, we assume a setting in which a negative shock increases the probability of entering treatment. And so this is a setting which parallel trends will not hold unconditionally, but will only hold after controlling for lagged outcome dynamics. These graphs summarize the results from running 200 replications of the first scenario where treatment is exogenous. So in these graphs, the gray line is an equally weighted average treatment effect, this one here, and the light blue shade gives the range of all the heterogeneous group-specific effects. In the left top panel, this one here, you can see the estimates from the two-way fixed effects event study specification. And you can see that here, because of these dynamic and heterogeneous effects, two-way fixed effects gets it totally wrong, does a terrible job in estimating the treatment effect path. To be clear, we have designed the simulation to maximize problems with two-way fixed effects regression. So in most settings, it will be two-way fixed effects regression will generally do better than this in most settings, but this is something that can happen when you have dynamics and heterogeneity. On the right top panel, this one here, you can see the estimates from our LPDID estimator, and this is the variance weighted version, so without doing the reweighting. And you can see that it does a good job tracking the average treatment effect path. The two graphs on the bottom use the two very popular estimators that have recently been proposed, Callaway-Santana here on bottom left, and San Abraham here on the bottom on the right. So they are two estimators from this recent difference in differences literature. I don't have time to explain in detail what they do, but basically they perform many clean 2x2 comparisons and then take averages over them. They also do quite well in this setting. They do very well. And here, in terms of root mean squared error, for example, our LPDID estimator does at least as well as the other two estimators at all time horizons. Then we have the second simulation, the one where the probability of treatment depends on past outcome dynamics. And you can see that in this setting, our estimator, which is the one that allows to control for past outcome dynamics, is the one that gets the answer right, while the others can't. And they can't because these other estimators are not designed to allow to control for lagged outcome dynamics. Now, I want to be clear that the point of this is not to claim that our estimator will be, superior to the others in general. The point is just to show that there is at least one important setting in which ability to match on pre-treatment outcome dynamics is important. And in that setting, there is a real advantage to the ability of our estimator to do that. So these other estimators are just not designed to address this type of situation.
Can I ask another question here? So as you said, it could be possible to use these two other estimators to deal with the endogeneity. Is that correct? Or
well, there is no straightforward way in using these other estimators to control for lagged outcome dynamics. And the reason is that the structure of these estimators, including two-way fixed effects regression, is such that if you include the lag of the outcome, that will not be measured pre-treatment. It will be measured post-treatment. And the reason is that in our LPDID estimator, we get dynamics on the left side of the regression by taking the long difference. And then if you take a lagged variable on the right side, that's measured before treatment. But if you think, for example, of the structure of two-way fixed effects event study regression, for example, for a unit, for which the lagged treatment indicator is equal to 1, then for that unit also the lagged outcome will be measured during the time of treatment. And so, you can't really control for lagged outcome if the lagged outcome is measured post-treatment. So I'm sure probably there are ways to adjust the Callaway-Santana and San Abraham to address this, but in the current version, they're just not designed to allow controlling for pre-treatment outcome dynamics. It has to do with the structure of the regression. Now, one thing, so as I said, that we're not claiming any superiority based on this, just that there is some setting in which you really need our estimator to be able to do this. Something I will claim is that our estimator runs much faster in terms of computational speed. So this is the time it takes to estimate the treatment effect path in a single simulation of the first data set where treatment is exogenous, using a good machine. And basically, our estimator takes 1 second to run and to compute the entire treatment effect path, which is similar to two-way fixed effects regression. But you can see that Callaway, Santana, and Sun and Abraham are much more, are much slower to run because they are, they have many more passages to make, and it takes 144 seconds for Callaway, Santana, and almost 200 for Sun and Abraham. If you have to do something like, for example, running a placebo test where you have to do hundreds of replications, this can be a real advantage of our approach, the computational speed. Now, the other thing I would like to show you is two applications in which we illustrate, using our estimator by replicating two recent studies. So the first one is an empirical application where we study the effect of banking deregulation on the labor share. Here, the context, briefly, is that between 1970 and 1996, US states deregulated banking at different points in time. So banking deregulation was introduced in a staggered fashion in the US, across US states. And there were two types of banking deregulation that were implemented. The first is called interstate banking deregulation. This means you make it easier for banks from outside your state to start operating in your state. The second type is called intrastate branching deregulation. It means you make it easier for domestic banks to open new branches in the same state. There is a recent paper published in the Economic Journal in 2020 by Leblebichoglu and Weinberger, which uses two-way fixed effects regression to estimate the effect of these banking liberalizations. And they find that the first type, interstate banking deregulation, has a substantial negative effect on the wage share, but the second type, intrastate branching, has no negative effect. These graphs summarize results from using two-way fixed effects regression to implement this design. So here in the top panel, you have the results from a static two-way fixed effects regression across different specifications. The blue bars show the effect of intrastate branching deregulation. You see, in that case, there is no negative effect. There is, if anything, small positive coefficients, but very imprecisely estimated. But the black bars, which show the effect of interstate banking deregulation, show a clear negative effect estimated by the two-way fixed effects regression. In the two bottom panels, you have results from an event study two-way fixed effect specification, which confirms these results, because you can see in the left bottom panel a negative effect, again, of interstate banking deregulation, and you can see on the right bottom panel that instead the effect of intrastate branching is estimated very imprecisely, but overall, there is no negative effect. Now, the potential problem with this is that here two-way fixed effects uses these forbidden unclean comparisons that I described earlier, which in this setting means that states that liberalize early in the sample are used as controls for states that liberalize later. So there is the potential for this bias that I described. So first thing we can do to assess the extent of the problem is to use a decomposition proposed by Goodman-Bacon, which assesses what is the influence of these unclean comparisons in which previously treated units are used as controls in the two-way fixed effects estimate. So this refers to the static two-way fixed effects estimate. And what you find by using this decomposition is that in the case of interstate banking deregulation, that one that has a negative effect, there is a significant influence of these unclean comparisons. They account for 36% of the estimate. But in the case of intrastate branching deregulation, this is the type of liberalization that, for which two-way fixed effects does not find a negative effect. In that case, these unclean comparisons account for 70% of the two-way fixed effects estimate. And using the Goodman-Bacon decomposition, you can also see this visually in graphs. So here, the left panel refers to interstate banking, the right panel to intrastate branching. And for each one, you see on the horizontal, on the vertical axis, the estimate from each 2x2 comparison. So basically each group effect that contributes to the two-way fixed effects estimate. And on the horizontal axis, the weight assigned to that comparison. So this, the Goodman-Bacon decomposition, is the one in which you see two-way fixed effects as combining all possible 2x2 comparisons in the data. And here in gray, the gray little points are the good comparisons, where newly treated units are compared with not yet treated units, while the black points are the forbidden comparisons, where earlier treated units are used as controls. So you can see that on the left side, in the case of interstate branching, there are many unclean comparisons, but they are on the left side of the graph, meaning that they receive small weight. And they tend to give positive estimates, but then there are all these clean comparisons in gray that tend to receive more weight and give positive negative estimates. But if you look at the right panel,
just for clarification here, so 2 slides before, you said the previous this paper that the previous people have treated this as a static environment. What does it exactly mean? How they? I think it was 1 slide before.
Yeah. This one.
Yes. So the paper in 2020 used static and event study. So what does it mean here exactly? What? How do they Are you in other words, are you using a dynamic setup? Is that one of the difference here?
Well, they use both, right? So here they use both a static fixed effects regression, and in a clean 2x2 setting, the static two-way fixed effects regression, even if the effect is dynamic, still a static two-way fixed effects regression will give you, the average effect averaging across all post-treatment periods. So if this was a simple 2x2 setting, even if effects are dynamic, you can still use a static two-way fixed effects regression to get an average treatment effect, which is an average over all time horizons. The dynamics themselves, if there is only one group, it would be still fine if you're interested in an average effect over the treated period to use static two-way fixed effect regression. And so I think this is what, because at the time, to be clear, when this study was published, we didn't know about all these problems with two-way fixed effects regression. People thought that it did in the staggered setting the same thing that it did in the 2x2 setting, and in that setting, it's fine. You can estimate this average effect. Does that make sense?
Oh yes, thank you. Very clear.
So what we see here, if you look at the right panel, and we come back to this, looking at the clean and unclean comparisons that contribute to the two-way fixed effects estimate, we see that here there are several unclean comparisons. So comparisons in which previously treated units are used as controls, which receive a very large weight in the two-way fixed effects regression, and they tend to give these small positive estimates. And in particular, these points, the ones that are black circles, they represent a particular type of unclean comparison in which units that were already treated at the start of the sample periods are used as controls. So these are states that probably liberalized banking just before 1970, so just before the start of the sample period, and then they are used as controls for all states that liberalize over the sample period. But the problem is that if the effects are gradual, then these states are not good controls because they are still experiencing the dynamic effects of treatment. So we have applied our LPDID estimator to address this problem and to, drop these unclean controls by using our clean control condition. And this is what we find. So if you look at the left panel, you can see that across different specifications, we do confirm the negative effect of interstate banking deregulation. So here we find an effect, kind of similar, a bit bigger in size, but similar to what is found by two-way fixed effects and the original paper. But if you look at the right panel, this is the effect of intrastate branching deregulation. Here we find the same type of negative effect, while with two-way fixed effects regression, the original paper found, if anything, positive coefficients. So this means that these unclean comparisons that received a very large weight in the two-way fixed effects regression were flipping the sign, but when you drop them and you only use only clean comparisons, you actually see the same type of negative effect as in the other type of liberalization. So this shows an example in which really these unclean comparisons can, mask the actual dynamics that you see post-treatment in the data. The other application that we have done is an application where we study the effect of democracy on economic growth, revisiting a paper by Acemoglu, Naidu, Restrepo, and Robinson, published in 2019 on the Journal of Political Economy. In this paper, they use a country-level panel from, they have data from 1960 to 2010, and they have a binary measure of democracy. Their outcome of interest is GDP per capita, so effect of democracy on GDP per capita. So this is an interesting application for us for three main reasons. First, that there is the potential for negative weights bias, meaning that countries that democratize early in the sample are then used as controls for countries that democratize later, implicitly in the two-way fixed effects estimator. Second, it is an example of non-absorbing treatment, because you do observe countries that can go in and out of democracy, can democratize, but then can, they can, become dictatorships again, they can slide back into autocracy. So it's an example of applying our estimator in a case where there is non-absorbing treatment. And third, here, controlling for pre-treatment outcome dynamics is crucial, because there is evidence of selection into democracy based on economic dynamics. And indeed, this is one of the main claims of the original paper. This is a graph that reproduces a graph in the paper. It shows GDP per capita around the democratization, where year zero is the year of democratization, and we see that democratization tends to be preceded by a dip in GDP per capita. Okay, so before a country becomes democratic, there tends to be a reduction in GDP. And one of the claims of central arguments of the original paper is that in order to estimate the effect of democracy, you really need to be able to account for this pre-democratization dip in GDP per capita. And so it's a way where we can show the ability of our estimator to control for pre-treatment outcome dynamics. This is the baseline specification from the original paper, and so they used a dynamic fixed effects model where GDP per capita in a country in a year depends on the treatment indicator, so an indicator for being a democracy, lags of GDP per capita, country fixed effects, and time fixed effects. And then they use the coefficients from the specification to extrapolate a long-run effect, which according to their estimates, democracy increases GDP per capita by as much as 21 percentage points over the long run. And this shows the impulse response function by extrapolating from the coefficients from their dynamic panel model. Now, here, as I mentioned, there is the potential in this panel two-way fixed effects regression to have bias because of the unclean controls. So we apply our local projections, difference in differences specification, or LPDID specification. And here is what we use in particular. So we have a specification where you have the long difference in GDP per capita on the left side, the change in the democracy indicator on the right side, time effects, and lags of GDP per capita. Here, the clean control condition, we adjusted to this setting. So it's a bit different from what I showed in general case. It's an example of how you can adapt this based on your setting. So here we define treated units as units that enter democracy. So change in the democracy indicator is 1. But the clean controls here are countries that have been non-democracies for at least capital H periods before time t, and remain non-democracies until t plus k. So the difference here with respect to what I showed earlier is that here we are not saying that instead of saying you just need to have no change, okay, in democracy status for capital H periods, here we are saying not only you need to have no change in the democracy indicator, but you need to have been a non-democracy for capital H periods. And the reason is that in this setting, also based on arguments in the original paper, it makes sense to compare countries that transition from dictatorship to democracy to continuing non-democracies, in order to address the fact that democracies and non-democracies may potentially be on different trends. So this is an example how you can adjust your definition of the clean control group based on the institutional setting. And in this case, it makes sense to only compare new democracies to countries that continue being non-democratic, rather than compare them with established democracies that may be on different trends. So interestingly, Acemoglu and co-authors in the original paper have a section where they apply for robustness a local projections specification, and they also apply some sample restriction that in a way is a version of what we do. So in a sense, their paper is a precursor to our LPDID estimator. However, they define the control sample as countries that are non-democracies at time t and at time t minus 1. So this is kind of like our clean control condition, but with two differences. First, they define a very, very narrow interval. So, countries that democratize at time t minus 2, can still be in the control group, even if they are probably still experiencing the effects of democracy. But also, they include countries that have changes in the democracy status between time t plus 1 and t plus k, which is during the horizon over which you are estimating the effect, which is something that our estimator excludes. But apart from these differences, the spirit is kind of similar. So to give an example of why this matters, take Spain that democratized in 1978, Ecuador democratized in 1979. When you estimate the dynamic effect of democracy over the long run for Spain, you don't want to use Ecuador as a counterfactual, because Ecuador enters democracy 1 year after Spain, and so it will be experiencing the same effects over the post-treatment time horizon. And our estimators excludes Ecuador from the counterfactual for Spain, but the original analysis does not, because they do not restrict the treatment indicator between t plus 1 and t plus k. So this is the results. So this is 4 different specifications. The red bars are estimates from the local projections specification in the robustness section of the Acemoglu and co-authors paper. All the other bars are our LPDID estimates with different time windows for defining clean controls. The main takeaway is that in this case, we confirm the positive effect of democracy as in the original paper, The only difference is that when you use this cleaner definition of the control sample, the long-term effects, say the effects after 20, 25 periods, become much more uncertain. And that's because we are being more strict about which units can be used as controls. And after all these time periods, there are so many countries that in the meanwhile have democratized, and so should be dropped from the control sample. So we show that here, when you're strict about the control sample, it becomes hard to estimate effects after the 25, years after democratization time horizon. So we just get more uncertain estimates, and there is some evidence, of some decrease in the effect. That's not in the original paper, but mainly it just it just says that if we are strict about the control sample, you can estimate effects only up to a certain time horizon. But overall, the takeaway is that in this case, we confirm the effects of the original study. So to conclude, I believe that the estimator we are proposing can be useful for applied researchers, because it offers this flexible framework for difference in differences that you can adjust very easily to the setting that you have in your data. And I think it's more transparent than other estimators. I think it's easier here to understand what you are doing, because you define this clean control condition and you know precisely how you are defining the treatment group and the control group. It also has advantages in terms of being less computationally intensive than other estimators. And then, as I said, if you need for robustness or in a main specification to control for pre-treatment outcomes or other predetermined covariates, then our estimator offers a very simple way to do it. I will conclude with this. Thank you so much for your attention, and I look forward to hear your thoughts, comments, critiques, and questions.
Okay, thank you very much, and thank you very much for the perfect timing. And I think we have enough time to take more questions. I would like to ask the online participants, if you have some question, please feel free to put in the chat.
Yeah, we have the Q&A chat, if I'm correct, is what we are using to collect questions, right?
So while waiting questions from the online participants, I have one question about the selection of the time window age. So I'm a corporate finance guy, so I'm like thinking, I'm thinking out to let's think that if I use this estimator in a situation that if I'm interested in firm leverage and how that could be respond to state tax changes. Let's think about the environment like that. How should I set up this age in that environment in the corporate finance setting? So should I add some stories, or should I change age in a very broad range to check the robustness? What is the guideline?
Yeah, so I think here there is some trade-off between being general in allowing for the lag defects to last long, and statistical power, because in these cases in which it sounds like in the setting you described, you will not have any unit that has never experienced that change in taxation, right? So it sounds like a setting which you cannot just do full clean controls in which only units that have experienced no change in treatment are controlled. So you're going to have to make an assumption. And here the idea is that you have to make an assumption about after how many time periods after treatment you can assume that treatment effects have stabilized, so that these units may potentially be on a different level because of the effect of treatment, but the trend is no longer influenced. by treatment. So you're going to have to make an assumption about, for how long the dynamics of the effect can continue to change over time. So
does that mean the persistency of the leverage could like affect the length of the time window?
Well, that's interesting. So are you thinking about setting in which different units can have a different time window, or I don't know the setting enough. So
okay, yeah.
Let's talk later. But I wanted to understand if you have in mind that different units may have a different like time window or something different.
Yeah, maybe, yes.
Yeah, I mean, that's super interesting. I never thought of it, and so I cannot tell you if and how it could be done, but it's something I never thought of and can be really interesting. In general, I think it's, if you can just consider the longest time window that you can have, so the units that have the the long lagged effects for the longest time, that time that the treatment effect continues to change, then just set the longest time window that will accommodate all this when it's possible.
Okay, so I think we don't see any further questions. So I would like to close the session. So thank you again for joining and giving a great talk, Daniel. I wish you could come to KL sometime, but
I hope I will.
Okay, so thank you so much.
Thank you, Iguo, and thanks everybody for attending. And I just want to add that if you have questions that you think about later on, feel free to to send me an email, or if you want to see if you can apply this to your data set, I would love to be in touch and answer any question or chat about this also over email or later on. Thank you so much. I know it's evening for you guys, so have a great evening.
Yeah, have a great day.
Bye.
Bye.